Hello all, welcome to the lecture on time complexity. So in this class, in this lecture, we'll try to understand what can and cannot be computed with limited resources. Okay, so this is opposed to what we have seen in the previous lectures, which is about um, as opposed to ideas like Turing recognizability and decidability. Which allowed us to reason about what can and cannot be computed. Okay. So here we'll be focusing only on problems that are decidable. Okay. And we'll be trying to understand among those problems that are decidable, which are the ones that can be computed or computed with limited resources against others that really need to take a lot of resources to uh, decide that particular problem. Okay, so our focus will be on decidable problems. Okay, and when we are talking about resources, there are many different resources that we may be interested in. So the primary resource that we'll be interested in is time. Okay, but you could also think about space. You could think about communication. Okay, and I mean, this is in case when maybe things are distributed, or even the amount of randomness, and so on. Okay. So broadly speaking, complexity theory is really the study of the amount of resources that is required to do various computational tasks. Okay, and in this lecture, we'll be focusing mainly on time. Time is the primary resource that we'll be focusing on. Okay, and this is really a very rich area with many challenges and problems that haven't been resolved yet. So there are many open questions, and this is really an extremely active area of research. Yeah, there are many big challenges that we still don't understand. Okay, with many open challenges. Okay, so maybe so for the rest of the lecture, here is the overview. So we'll first define time complexity formally, okay, in the context of Turing machines. And then we'll talk about how, we'll talk about these different complexity classes, which try to capture, which really tell you how there is more power that comes with more time. So this is really a valuable resource for computation. Then we'll also talk a little bit about the robustness in the definition of time complexity across different models. So there may be different models of Turing machines that you can pick, but we'll see that really this notion of time complexity is fairly robust. And finally, we'll talk about the concept of polynomial time computability. And this is this important class called P, which you may have heard about in other courses like algorithms. Okay, but this is a central focus of attention in complexity theory and algorithms. Okay, so this is the plan for the rest of this lecture. Okay, so let's start by talking about by defining time complexity of time complexity. In particular, we'll be talking about time complexity of a Turing machine first. Okay, so measuring time complexity of a Turing machine. Okay, and really the thing you want to do is you just want to count the number of elementary steps that is required by the machine to halt. Okay, so let M be a Turing machine that halts on all inputs. Okay, And remember, we are only focusing on decidable problems. Okay, so let's think about a Turing machine that halts on all inputs. Okay, now the time complexity will be measured in terms of the input. Okay, in particular, the size of the input. Now, the size of the input can actually depend a lot on the problem. So there may be various parameters for a problem. For instance, if you think about a graph problem, then different parameters could be the number of vertices, or the number of edges, or yeah, the degree of the graph, and so on and so forth. Um, but what we'll do in this lecture and throughout this course is we'll just focus on, we'll use the size of the description of the input as just the input size. Okay, so the input size is just going to be the size of the description of the input. Okay, and this is really what this is consistent with what we do with Turing machines. So we just think of the input as being a string, okay, over some alphabet, let's say 0, 1. And really the size of the input is just the length of the string that represents that input. Okay, so here is the definition of time complexity. Okay, so the running time or time complexity of this Turing machine M is really a function. Okay, it's not a number, it's a function which depends on the input size. It's a function f that goes from natural numbers to natural numbers, okay, such that f of n is equal to the maximum number of steps okay, taken by m over any input of length n. Okay, so let me box this. Okay, so this is the definition of the time complexity of a Turing machine. Okay, so one thing that's important to note here is that is the focus on any. Okay, so we are going to look over all the possible inputs of length n, and f is actually going to be the worst among all those inputs. So this is really a notion of worst case analysis. Okay, so for a Turing machine M, you look at, and for a particular input size small n, you look at all possible inputs of n, of size n, and f of n is exactly the time complexity of n is just going to be the maximum number of steps that the Turing machine takes, okay, over all possible inputs, size n. So this is the worst case notion of complexity, and this is what we'll traditionally use. And this is what is traditionally used in computer science, theoretical computer science. Of course, there are other notions that are used as well. That could be an average case notion of complexity, and there are things that go beyond worst case analysis, but that is out of the scope of this course. Okay, and the second point I'd make is that here, when we talk about time complexity, we'll predominantly use the big O notation. Okay, and this is consistent with how you analyze algorithms as well. Similarly, when you're talking about the time complexity of a Turing machine, you use the big O notation. And this is something that this is something that's covered in one of the review lectures. Okay, so see review lecture about it if you have any questions. Okay, so this is the time complexity of a Turing. Now let's look at an example. Okay, and let's look at this language that we have considered before, which is the set of all strings consisting of zeros and ones where you have a set of zeros followed by an equal number of ones. Okay. And yeah, I mean, of course, k is the natural number here. Okay. And remember, this was a language that was not regular. However, you could construct a Turing machine for this task. Okay, now here's a simple Turing machine that implements this, that recognizes this language, in fact, decides this language. In fact, here is a pseudocode that represents this Turing machine. So on an input of size n, let me just, I just copied it just to save some time. On an input of size n, what this Turing machine does is you just scan across the tape first, okay, do one scan of the input to ensure that the input is just consisting of a string of zeros followed by a string of ones. Okay, here you're not checking if the number of zeros and ones are equal. You just want to see that it is of the form a bunch of zeros followed by a bunch of ones. And that's the first step. Okay, and the second step is to basically repeat the following, where you go from across the tape and you kind of cross off a single zero followed by, and then you go across the tape to where the one start, and then you cross off another one. Okay, and then you come back, cross off yet another zero, and then you go and cross off an uncrossed one, and so on. Okay, you just keep doing this. Okay, and this is the Turing machine that we've seen before, and then finally, if any zeros remain uncrossed, and but all the ones have been crossed, okay, or if there are ones remaining and all the zeros have been crossed, then you reject. Otherwise, none of the zeros or the ones are left uncrossed, in which case you accept. Okay, this is the Turing machine that we've seen before. Let's just analyze the time complexity of the Turing machine. Okay. Well, the first step is, so we scan across the tape just to check if it is of the form a bunch of zeros followed by a bunch of ones. And this, one second, that's strange. Okay, so let's just continue writing. So this step takes time, which is order of n, because the input is size n, and it just scans. It's just one scan across the input. Now the next step is a little more interesting, okay, because you keep going off and crossing off 1 0, and then followed by crossing off a 1, where you go across the tape. And then you come back and cross off another 0, and then you again go across the tape to cross a 1. And so each time you cross off a 0 and a corresponding 1, you may have to go across almost the whole tape. So that's an order n step. But that's for crossing off 1 0 and 1 1. Okay, but you have to do this for roughly n over 2 zeros or so. Okay, and n over 2 1. So this is an order n squared operation. Okay, then finally, you're just going to check if there is any zeros remaining or ones remaining. And again, this is potentially, and you just need to do one scan of the tape. This is an order n operation. Okay, so the time complexity of this Turing machine, remember, is the worst over all possible inputs. Okay, and of the time it takes on input n, and the time complexity is hence order n squared. Okay, good. Okay, so that was the time complexity of a single Turing machine. Okay, but now let's try to extend this concept from, particular Turing machines to languages. Okay, so we'll see the idea of this leads us to the idea of time complexity classes. So the goal is to classify languages, okay, by their time requirements. Okay, so here's the definition. Okay, so I write it in different color. Okay, so the class time. So think of small t of n as just a function of n. So the class given by time of this function t of n, okay, is really the set of all languages L prime, okay, such that there exists a Turing machine, okay, M, with time complexity order t of n, okay, which actually accepts this language. So L of M should be equal to L prime. Okay, so one thing that's important to note here is that this consists of all languages for which there exists a Turing machine which has complexity at most order t of n. Okay, so there might be Turing machines for this language that could take actually more time. Okay, but for among all the Turing machines that accept this language, you can choose the minimum, the one that has the least time requirement, and then if its time requirement is given by the function t of n, then this language is in time of t of n. Okay, so for example, okay, this language A that we looked at, which was given by strings of zeros and ones, where you have zeros for bunch of zeros followed by an equal number of ones. This language we just proved is in time n squared. Okay, so here t of n is the function n squared. Okay, now because this is in time n squared, it is also in time n cube or n to the 4 or any larger function than n squared, because note A is also in time n cube or anything else, okay, anything higher, because this is still, since n squared is still order of n cube, okay, according to the big O notation. Okay, so it is certainly in larger time complexity classes, but typically you want to find the smallest function t of n for which the language actually, where the language resides. Okay, so good. So this is a notion of, this is time-bounded complexity class. Okay, sometimes this is also referred to as, referred to by, d time t of n. This is just an alternate notation. Okay, and we will see why a little later. Okay, this just stands for deterministic time. Good. Okay, so now we know that the class A resides in time of n squared, in the class time of n squared, but it perhaps also resides in a time complexity class which corresponds to the smaller time requirement. For instance, so the really question is, maybe there exists a more efficient Turing machine for A. Okay, and it turns out that the answer is yes. You can actually do something more efficient, more interesting. Okay, and we'll just see this. Okay, so recall that A is the language given by 0 to the k, 1 to the k. K is a natural number greater than or equal to 0. Okay, so actually, so we saw a Turing machine before for this, which which basically scanned through the input and then crossed off for every 0. You went and crossed off a 1 and then came back, crossed off another 0, went and crossed off another 1. But you can try to be more efficient about this. When you cross off a 0 and you go and cross off a corresponding 1, you have to go all across all the other zeros, and then before you go and cross off a 1. But maybe if you can cross off multiple zeros at a time, then you can be more efficient. And this is what the algorithm will actually do. Okay, so let me actually show the pseudocode for it. And in the interest of time, let me just paste the pseudocode for it. Okay, good. So this is the algorithm. Okay, so as before, the first step is to just scan through the input and check that the string is actually of this form, 0 to some bunch of zeros followed by a bunch of ones. Okay, but now it's going to do something more interesting. Okay, first you check if the parity of the number of zeros, okay, is equal to the parity of the number of ones. If it is not equal, you just reject the string. Okay, so for instance, if you have 10 zeros and 13 ones, then the parity of 10, which is even, is not equal to the parity of 13, and so you just reject. On the other hand, if it has 10 zeros and 12 ones, you're not going to reject at this step because the parity is both even. Okay, so this is just a check that you do. Okay, and then here's where you do something more interesting. You basically cross out every other 0. You're not crossing out just one 0 and then going and looking for its partner 1. You cross out every other 0, every alternate 0. And then you go to the ones and you again cross out every other 1. Okay, and then you basically kind of keep repeating this. Okay, so you do this, and then you go back and you check if all the bits have been zeroed out. Okay, and you check if the parities of the zeros, the remaining zeros, is equal to the parities of the remaining ones or not. If they're not equal, you reject. Otherwise, you go ahead. And then you keep doing this until all the bits have been crossed out. And at the end of it, when all bits have been crossed out, you accept. Okay, good. So let's see an example. Okay, so that just to make things a little clearer. Okay, so let's look at a string where maybe there are 8 zeros and 8 ones. Okay, so this is something that is in the language. Okay, recall that. Okay, this is in the language. Now, what does the algorithm do? It scans across the tape, and first, you check that the parity is the same. Okay, second, let me just get one of these different colored markers. Good. Now you just first check that the parity is the same for the zeros and the ones, and they're both equal. In fact, they're both equal to 8. So if the number of zeros is actually equal to the number of ones, you will always be fine in that step. Okay, and now what you do is you go and strike out alternate zeros. So you cross out the first 0, then the third 0, then the fifth 0, seventh 0. Similarly, you cross out alternate ones. The first one, the third one, the fifth one, and the seventh one. Okay, now go back and check if, okay, there are still some zeros and ones to be crossed out. And then you check if the parity of the remaining zeros, and the remaining zeros is 4 of them. Okay, so it's this one, this one, this one, and this one. There are 4 zeros left and exactly 4 ones left. So the parity is still the same. Okay, now you go in and you start crossing out, again, alternate zeros among the remaining ones that are left. So you cross out the first remaining 0 left. You will not cross out the next remaining 0 left. Again, cross out, okay, the third remaining 0 and leave the fourth one. Similarly, for the ones, cross out the first one remaining and then third one remaining. Okay, so now how many zeros are left? This one is left and this one is left. Similarly, among the ones, this one is left and this one is left. Again, the parity is the same. You continue and you cross out maybe another. Cross out the first 0, leave out the second one. Similarly, cross out the first one, leave out the second one. Okay. Again, the parity will remain the same. This is left and this is left. And finally, we cross out this one and this one. And now all of them have been crossed out. So, so this is in the language. On the other hand, if it had been a different number of zeros, okay, one, let's try it with 10 ones. Okay, in the first step, you cross out the alternate zeros. So this will cross out all of these and then cross out alternate ones. Okay. So now the remaining ones have how many of them? There are 4 of these zeros. And how many ones are left? 1, 2, 3, 4, and 5. So the parity is not equal at this step because there are odd number of zeros left and an even number of ones left. So this is not in A. Okay, so this is the algorithm. Okay, good. So, and what is the time complexity of the algorithm? Well, the first step is still going to take order and time because it's just doing a scan across the whole tape. Okay, now let's look at the second step. Okay, now the key thing here is that in every step, okay, in every iteration, I mean this whole sequence of crossing out things, half of the input is scratched out. Okay, so in every iteration you may take order n time, okay, to go across the input. It's essentially a scan. Okay, but half of this is scratched out, and half of what is remaining is scratched out. So the time complexity in total is order n log n. Okay, since in every iteration half the input is scratched out. At least half the input. It could be more. Okay, hence there are only order log n iterations. And this gives a time complexity bound of order n log n. Okay, good. So this says that A is actually in time of n log n as well. Okay, good. It is in time n squared, but it is also in fact in time n log n. Now here are a few remarks about this. Okay, it turns, you could ask, well, could there be an even more efficient algorithm? Okay, maybe it's in time complexity class, time of n. Maybe there's an order n time algorithm. Okay, or maybe something between n and n log n, or even smaller. It turns out that the time complexity is actually n log n, and in fact, you can show that any one-tape Turing machine, which is the usual Turing machine that we have looked at so far, can't decide A and little o in any smaller time, that is asymptotically smaller time. In little o of n log n, it's impossible. Okay, this is something that can be shown, and we're not going to show it here. Okay, and in fact, there's something stronger that you can show, and this is an exercise in Sipsert's book, because since it turns out that the only languages that can be for which you can construct a one-tape Turing machine that decides it are regular languages. Okay, so one-tape Turing machine that decides it in little o of n log n time, okay, are regular languages. Remember, n is the size of the input. Okay, so this is an interesting lower bound for one-tape Turing machines. And here's another point which is something that, yeah, I mean, you may have seen in one of the lectures already, I mean, on Turing machines. But recall that regular languages are precisely those languages where the number of states is finite. Okay, it's really a constant. Okay, and you just have your input and it goes through, the whole input like a stream. Okay, so regular languages are exactly those languages for which you can construct Turing machines which only need order and time. Okay, so what I'm really saying is that regular languages are in time in the complexity class time of n. So what this is really saying is that between time n and time n log n, just a little less than n log n, okay, little of n log n, there's really not that much power that you get. Okay, so by the way, I'll leave this as an exercise, okay, to figure out formally why this is the case. But once you go to n log n, you are starting to recognize these languages like a bunch of zeros followed by an equal number of ones. Okay, and so you seem to, which is certainly not regular. So you seem to get much more power. Okay, so good. So you see that there is more power that comes from going from order n to order n log n. Do you always get more power now when you go from, let's say, n log n to n squared to n cubed, and so on? Okay, and this leads us to what is known as the time hierarchy theorem. Okay, which is a very, which really tells you that with more power, with more time, you get more power. You can solve strictly more problems. Okay, so here is a theorem, and in fact, we are not going to see a proof of this theorem. I'd encourage you to read Sipser to see a proof of this theorem. So basically, here's a theorem for reasonable f and g, and there's a very simple condition that, it's a condition that you need to satisfy, where g of n is some larger function than f, but in fact something slightly, quite a bit, just a little bit more larger than just saying that g of n is greater than f of n. You want it to be larger by an extra amount, which corresponds to this log squared n. Okay. Then you can say that the time complexity class that corresponds to f of n is a strict subset of the time complexity class that corresponds to g of n. Okay, so g of n is something that is a little larger than f of n. Okay, now the fact that it is a subset is not the interesting part. The interesting part is the fact that it's a strict subset. Okay, so it says that it's not equal. And that's the interesting part. And this proof is using, in fact, the proof is using diagonalization. Okay, and this is actually theorem 9.10 in Sipser. So I'd encourage you to look at it if you are interested in the proof. Now, here's a simple corollary of it, which I think is quite interesting, and like it's useful. And yeah, this is a good way to remember it as well. So corollary, you can think about these functions f and g as, for instance, you can think of f as being n and g as being n squared. Now the condition is just saying that n squared should be much larger than f of n, which is n times log squared n, which is true. Okay, so so this really says that time of n is a strict subset of time of n squared. And similarly, the time of n squared is a strict subset of time of n cubed, and so on. Okay, so this really says that there's an infinite hierarchy of problems, okay, with respect to time complexity. However, I mean, this only tells you that there are languages that belong to, let's say, time complexity class n squared that don't belong, sorry, that belong to time complexity class, let's say, n to the 10 that don't belong to time complexity class, let's say, n squared or even n to the 9. Okay, but I mean, an interesting question, which is in fact quite open, is are there natural, I mean, or important problems that we actually care about that are high up in this time hierarchy? Okay, so this time hierarchy theorem only tells you that there are languages, but maybe, I mean, these are probably not the languages that we think of as, I mean, these don't correspond to natural problems that we care about, okay, particularly higher up in hierarchy. And figuring out these kind of problems is actually, I mean, a research challenge. Okay, so now let's move on to this question of, okay, so we have defined time complexity with respect to single tape Turing machines. Okay, we have seen that there are many other variants of Turing machine, for instance, multi-tape Turing machines and so on. Now, do these concepts, extend, I mean, is there some robustness with respect to time complexity? I mean, across these different models that we saw with respect to, let's say, computability, we saw that, the set of all languages that can be computed or decided by Turing machines. I mean, it doesn't really matter whether you're talking about single tape or multiple tape. And is that the same when it comes to this more fine-grained way of measuring time complexity? So robustness across different models or variants of Turing machines. Okay, so that's the next topic that we're going to explore. Okay, to answer this very succinctly, well, it turns out that the time complexity can actually change when you look at a slightly different variant of Turing machines. Okay, so let's look at an example. Let's look at our favorite example, which is the language consisting of, this language A that we have looked at a couple of times before. Okay, so here's a theorem. The language A, okay, can be decided in order and time using a two-tape Turing machine. Okay, recall that with one tape, it's impossible to do that. You can't even go below n log n. Okay, but for the two-tape Turing machine, you can actually design a simple algorithm which just takes order and time. Okay, and here is the. Okay, so here's the pseudocode or the proof idea. Let me only sketch it. In fact, so let me actually just copy paste the pseudocode to save some time. So like before on input of length n, the first step is just going to be, instead of just scanning over the whole tape, now we remember that we have two tapes, okay, in our control. So we just scan all the zeros, okay, and then copy them onto, the second tape. Okay, so just go through all the zeros that come at the beginning. Okay, so again, we're only going to look at all the zeros that come before the first one. Okay, just scan through them and then copy all of them onto the second tape. Okay, now what you do is for, if you want, you can just add another step, which is, just ensure that it is always of the form bunch of zeros followed by a bunch of ones. So you can just scan all the zeros, put it into the second tape, and this only takes order n time. And now what you do is you now scan through all the ones, and for each one that is scanned, cross off a 0 from the second tape. So remember that you have two heads because you have two tapes, right? And now, when you cross off a 0, you also cross off a 1 and you move both heads, right? So again, cross off a 0, cross off a 1, and so on. So these heads go simultaneously, and it's only going to take order n time. Okay, so the time complexity, so time taken is order n for a two-tape Turing machine. Okay, so the takeaway is that this. So in fact, this gap can be, can be larger too. Okay, so the takeaway is that time complexity. So let me say that the exact time complexity can depend on the model. Okay, and in fact, this gap can be quadratic potentially. Okay, and the language, for instance, that has this quadratic gap is, for instance, the language corresponding to, repeated strings of the form W followed by W. Okay, this is again not a regular language, and in fact, for this as well, you can show that the gap is quadratic. But what we're going to see now is that while this gap can be quadratic, it can't actually be worse than that. So that is really it's not the time complexity is not exactly the same, but there is an approximate equivalence. Okay. Okay. Let me just use. So an approximate equivalence exists. Okay, and this is a theorem. And this is not just for two-tape Turing machines, for multi-tape Turing machines. So it's true for multi-tape Turing machines. Let T of n be a function of n. Okay, and we are going to assume that it's at least n. Okay, this is a very minor condition. Then every T of n time multi-tape Turing machine has an equivalent order T of n the whole squared time single tape Turing machine. Okay. And see Sipser theorem 7.8 for proof. Okay. And really, I mean, the proof is not very complicated. It actually just uses the same simulation that we saw for, we had a simulation argument that showed that multi-tape Turing machines and single-tape Turing machines compute the same, can recognize or decide the same languages. Okay. And you're just going to use the same proof. Okay, so we're going to use the same simulation argument that we saw for simulating a multi-tape Turing machine by a single-tape Turing machine, and you can actually show that each step in the simulation, okay, so for each step of the multi-tape Turing machine, okay, that simulation will require at most the amount of time that corresponds to the total length of all the tapes, the sum of the lengths of all the tapes. And the sum of the lengths of all the tapes is also at most T of n. So for simulating each step of the multi-tape Turing machine, you can do this in time, which is at most order T of n. Okay. And there are T of n steps. So this in total gives you order T of n squared. Okay. But I'm not going to go into this full proof because it looks into the simulation argument again, okay, which we have seen already. Okay, good. So the main takeaway of this is that there is a robustness in the definition. Okay, so I mean, as a corollary, for instance, okay, you could say that, okay, suppose um, L is a language that takes for which you can design a multi-tape Turing machine takes time given by that is at most P of n, where P of n is a polynomial. Okay, so this is a polynomial P of n. Okay, so then it also has, then L also has a single tape Turing machine that has time complexity polynomial n. Okay, the reason is that there's only a quadratic blow up in the time complexity, okay, between a multi-tape Turing machine and a single tape Turing machine. So if you manage to show that there's a multi-tape Turing machine whose complexity is time complexity is polynomial, then that also means that there's a single tape Turing machine whose time complexity is going to be that polynomial the whole squared, which is also a polynomial. So there is this robustness in the definition. Okay, there's only a quadratic or a polynomial blow up, so it's really closed in this. Yeah, I mean, right. Okay, if you know that there was a polynomial time Turing machine which with multiple tapes as a polynomial time Turing machine with a single tape. And this naturally leads to, so yeah, so there's this robustness across different models, and that's also true for other models of various other models of Turing machines that you've seen. Okay, except non-determinism, which we'll see maybe in the next lecture. Okay, so this robustness in the definition leads to this class, which corresponds to those languages which can be computed in polynomial time. Okay, so this is the class which is called P. Okay, it's the set of all languages that can be computed in polynomial time. So it's a union of all the languages that belong to the time complexity class n to the k for all natural numbers k. Okay, so you look at all the languages that belong to n squared, n cube, and I mean, remember that this is an inclusion, right? Like, I mean, time of n squared belongs to time of n cube and so on. You just want it to be, you just want it to be inside the class time of some polynomial of n. Okay, so the exponent just needs to be some constant. Okay, good. And so as long as your language has some Turing machine that runs in polynomial time, it belongs to this class P. So this really captures a notion of efficiency. Okay, so these correspond to all problems for which you can actually design an efficient algorithm. Okay, and I mean, and this and the nice thing is that because you only care about whether it is polynomial time or not, it is also robust across different models and definitions. Okay, so in practice we may care about whether it actually takes linear time or quadratic time and so on. That may be a big difference, but up to a first order approximation, this is this actually really gives you a very nice definition of what is efficient and what is not. Okay, so let me say that up to a first order approximation, this actually captures all those problems for which you can actually design an efficient algorithm. Okay, the nice thing is that it can also be defined in terms of other kinds of in terms of multi-tape Turing machines, for instance. Or single tape Turing machines, and they're really going to be the same thing, because we know that going from one to the other only involves a polynomial blow up, which is fine according to this definition. Okay, so you could have defined it either in terms of single tape Turing machines or multi-tape Turing machines. The definition is going to be the same, and this notion is going to be is actually an extremely useful notion of efficiency, and this has actually led to a lot of developments in this field of complexity theory. Okay, and in fact, the fact that there is this robustness in this definition across different models of Turing machine, it leads to something called the extended Church-Turing hypothesis. Or extended Church-Turing thesis. Okay, which says that this notion of efficiency, I mean, it doesn't actually depend. I mean, it actually captures your intuitive notion of efficiency in any model. Okay, so it really says that a Turing machine, I mean, more generally, it says that a Turing machine can simulate every reasonable model of computation with only a polynomial blow up, a polynomial increase in time. Okay, so this we have seen in the case of multi-tape Turing machines, and it's true for some other variants that we have seen. But the thesis really tells you that, I mean, it's a strengthening of the original Searchturing thesis, which was just saying that Turing machines can capture, I mean, any model of computation that you can think about. Here, it kind of quantifies it by saying that you can think about any reasonable model of computation, and Turing machine can simulate it. Okay, with only a polynomial increase. Okay, it actually quantifies the amount of increase in the time. So this really tells you that, I mean, every intuitive notion of efficient algorithms is captured by polynomial time Turing machines, which is really our class P. Okay, I must say that this extended Searchturing thesis is, I mean, it's a strengthening, and it's also a little more controversial than the original Searchturing thesis, and maybe it's particularly in the light of like possible counterexamples. I mean, and one such, something that's not still understood is quantum algorithms, where we do know efficient quantum algorithms for problems like factoring, whereas we still don't know any efficient polynomial time algorithm for factoring in the Turing machine model, the classic model of computation. Okay, and we don't know. A few years down the line, someone may actually come up with a classical algorithm for factoring, which would show that it's in P. But currently, we don't know such algorithm, and I mean, maybe people also believe that no such classical algorithm exists. In which case, yeah, this questions the validity of the thesis. But I mean, but there has been no contradiction to the thesis so far. Okay, and this is the extended Searchturing thesis, and this is, I mean, by and large, this has really stood the test of time as well. Okay, so let's summarize what seen. This notion of time complexity of Turing machines. Okay, and we also define time complexity classes. These were the classes of the form time of some f of n. And we saw that more time corresponds to more power. Okay, and this is something that we saw in the context of the time hierarchy theorem. And there is also this robustness in this definition across different models. Okay, and we saw that even if you look at different models like multi-tape Turing machines, these time complexity notions are polynomially related. Then we looked at a particular class called P, which captures problems with efficient algorithms. Okay, I must mention that there are also, this is not the only class that we'll care about. In complexity theory, you do care about other classes as well. Maybe one thing to mention going back is, there is, for instance, a different class called exp, which is maybe the set of all, it's a sorry, there was some, which is, for instance, the set of all problems for languages for which you have exponential time algorithms. So this is 2 to the n to the k. Okay, versus remember that P is the set of all languages for which you have polynomial time algorithms. Okay, so I should have said this was time of 2 to the n to the k versus here this is time of n to the k. Okay, and exp is another class that you might see later on in this class, but the class P captures all these problems with which we think have efficient algorithms. Okay, and then we finally looked at the extended Searchturing thesis, which tells you that this is, I mean, which really tells you that P is the set of all problems with efficient algorithms, and it really shouldn't depend. It doesn't depend on the model of computation that you're thinking about. Okay, thank you.